We're a spin-off from the Boston Computer Museum. We have a mission to preserve and collect the historical artifacts of the computer and information age. We've moved all of the historical computers from Boston out to Moffett Field, and we're planning on building a proper public museum of computers and computer history at Moffett Field. And a lot of what we get involved in is all the electronic computers that, of course, we're involved in studying and designing and using here, but there was a prehistory before electronic computing of mechanical computing. But a lot of the concerns of the people in Iron Valley as opposed to Silicon Valley back in the 19th century were the same. All right, then you can have a microphone.
Just continue.
Okay. For example, Babbage was basically an engineer. He was probably well suited to be a CTO or a VP of an R&D in some company, but he found himself the CEO of a concern, and what he was trying to do was to raise money and do the marketing and do the engineering and produce a product. Well, he failed. He was not able to raise the venture capital to get his engine built. He was not able to do the appropriate marketing, and he was not able to build the engine itself. And what he wound up with was a pile of paper. So one of the valid historical questions is, what was his design, and would his design have ever worked? And one way to test the hypothesis that his design would or wouldn't have worked is to try to take his original plans and build it. And that's exactly what our speaker today has done. Doran Swade is Senior Curator of Computing at the London Science Museum, and one of the projects he started almost a decade ago, I guess, was to reconstruct the Babbage engine from the original drawings and to try to answer the question of whether Babbage was a crackpot without ideas that might have worked, or whether he was just a bad entrepreneur and not able to raise the money from the venture capitalists of the day. Doran is probably in a wonderful position to answer that question because he's simultaneously an engineer and an historian. The first half of his career was as an electronics engineer, and then he made a mid-career shift and became an historian, and has been, as I said, curator of the London Science Museum for many years. He's written extensively in the field of computer history. He's written 2 books on Babbage. A 3rd book on Babbage and the construction of the engine has just been finished in manuscript form to appear later this year. And he's going to tell us today about the Babbage engine project. Please welcome Doran Swade.
Thanks very much, Len. I understand from the orientation of the people present that they may be more interested in the technicalities of the engine than in the actual historical context of Babbage's efforts. But I'm afraid there's some medicine that I'm going to have to administer, and that is some history, because if there is a message about this Babbage's efforts at all, it is something that may be familiar to you, but is perhaps worth repeating, and that is that the fate of innovation depends on issues that are other than the technical merits of the invention. And if there is a lesson from Babbage at all, it is to do with that. So I'm afraid aspects, the unpleasant aspects of medicine and history need to be administered, because actually why his engines are the way they are and not otherwise, and that is unfinished, is inseparable from the context of his times. Who he was, who he knew, his personality, the vendettas, the personal conflicts were actually an inseparable part of the story of why it is he failed. In other words, there is no technological determinist, specific, simple answer as to why he failed. And what we'll do in the course of the afternoon is actually explore some of those issues. So much for preliminaries. So I apologize for the history, and I will continue to do so, but it's a necessary element in the story. Babbage is celebrated as the great ancestral figure in the history of computing, and almost every lecture about Babbage starts with a statement of that kind. He is famous equally for 2 things: for the genius of inventions, for the genius of his inventions and his failure to build any of them, and his name is inseparable from failure. In the absence, his name is inseparable. I mean, Babbage and failure, genius and invention are all sort of one package. It's one scrambled egg. In the absence of a demonstrable engine, I mean, he committed everything. He staked everything, his reputation, his self-esteem, civil honors, money, on one single gamble. And that is, he said, judge me by my engines. And he failed to build them. He failed to communicate a vision he had, an absolutely committed vision of what automatic computation was capable of. He failed to communicate it to his peers. He was deeply embittered by the absence of recognition, the failure of civil honors, and you will see we got some inkling in the process of building this machine as to just how extreme that disappointment must have been, because it's only through the process of building the machine and actually witnessing it, and you'll have an opportunity of seeing a video of the machine, that we began to understand the frustration and the despair he must have felt in his inability actually to speak to anyone about what it is he was doing. He was unable to communicate this vision, and therefore he was, as it were, the first inhabitant of a completely foreign country. The reasons for his failures. Every book on the history of computing will have a chapter or a passage in Babbage. And almost without exception, you will read the same thing. Babbage failed because of limitations of Victorian machine tool technology. Almost without exception, that is the received perception. Where people go further, they say, and often they don't, there's just it's either the implication or the explicit suggestion that the reason the limitations of Victorian machine tool technology entailed that he could not make parts with sufficient precision that when the machine was built it would work. So people either imply that or they specifically state it. Now, there's something very comforting in this thesis of limitations of technology. From the high ground of microelectronics, it's easy to patronize Babbage. Babbage had to wait for us, the children of the Silicon Age, to rescue him from his world of cogs and levers and wheels. E.P. Thompson, the historian, warned. He warned against the enormous condescension of posterity, this tendency actually to regard all that was past as somehow inferior. And I think that through the, so credible as this thesis is, and attractive as it is to us, he failed for limitations of technology. It's like the causes in science. It's a single cause, it has a direct effect, failure. Credible as this thesis is, and attractive it is to us, and as self-congratulatory as it is to us, silicon is in fact was the legacy, if you like, of Babbage. Attractive as it is, there is absolutely no contemporary evidence that limitations of technology was in fact a limiting factor if limitations of technology is equated with limitations of precision. Measurements done on contemporary machines show that they were capable of repeatability of 1.5 thousandth of an inch. That is to say, if you gave Joseph Clement, the engineer, a part, however intricate, they could make other parts within 1.5 thousandth of an inch. The issue is 1.5 thousandth of an inch enough? That's a highly precise thing. This was England, the workshop of the world. And what we will look into, one of the issues we had an opportunity to evaluate is the extent to which precision was or was not an issue. The fact is that the circumstances surrounding the collapse of Babbage's major efforts to build his engine, he conceived of the engine in 1821 and he spent over a decade of design and development building this machine. The circumstances surrounding the collapse of his efforts in 1833 do not owe anything implicitly or explicitly to limitations of technology. The circumstances are complex. He had a dispute with his engineer, Joseph Clement, over compensation for moving the workshop from Lambeth to a special fireproof workshop in the grounds of Babbage's house. So the circumstances were complex, and when you remove the technological determinist argument, when you say, okay, if it is not the limitations of engineering precision, what was it? You come up with a very, very complex, rich historical story. And there are many elements to the story. One of them is personal vendettas. The de facto advisor to government, George Baudelaire, the royal astronomer, persistently and consistently was opposed and hostile to the utility of these engines. In other words, experts were disagreed whether these engines had any fundamental utility. Other experts disagreed. Sealander in Sweden said, why do you need engines that can calculate to 30 or 50 decimal places? One of his machines has double precision arithmetic, multiplying a 50-digit number by another 50-digit number, the 100-digit result. Why did you need precision of this kind when you could only measure to 3 or 4 figures of accuracy? So experts were disagreed about fundamental utility. So it wasn't as though there was a universally accepted problem to which there was a solution that was needed. Personal vendettas. Babbage was convinced that Airy's hostile advocacy of his engines and his advice to government that the engines were worthless was based on a personal hostility of jealousy and a particular court case in which Babbage acted as an expert witness against the party that was being advised by Airy. And Babbage makes these allegations public. The specifics of it don't matter. The point about it is that there are all these rather peculiar factors involving personalities, vested interests, that affected the fate of the engines other than specific merits of the technology. Runaway costs. There was little credible progress. After 11 years, he'd manufactured about 10,000 parts of the 25,000 needed. He had nothing to show. The government invested vast sums of money. This money was unmanaged. There was no ceiling. There was no budget. There was no delivery date. There were no staging posts. There were no phasing of stage payments and all the rest of it. It was wonderfully muddled and terribly English. I mean, it's inconceivable in this day and age with this obsession about cost efficiency and all the other manager's gobbledygook that this gentleman's arrangement about funding a project to completion on a drip feed basis could ever have come about, but it did. So the fact of the matter is that the limitations of technology, attractive as that thesis is to us, is not a specific feature that featured in the contemporary circumstances that resulted in the collapse of the work. Clement downed tools after payment about compensation, and work was never resumed. in 1833 after about 10, 11 years of design and development. So the point about this is that the question that becomes very tantalizing to historians is, did the complex circumstances surrounding the collapse of the project to build the machine mask the technical or logical possibility, feasibility of these machines? In other words, have people been distracted by either... The question is, if people accepted that limitation technology was the reason, and it turns out it is not the reason, did the circumstances surrounding the collapse mask the fact that these engines could not have been built? In short, the question is, could the machines have been built in Babbage's day? And secondly, if they had been built, would they have worked? And that is the issue we actually set out to address. I promised that you would have some medicine before we get on to the technology, onto the actual specifics of the machine. And so, because the fate of the engines is inseparable from the context of Babbage's times, I'll just give you a quick thumbnail sketch of Babbage's life. Who was he? What was the context? What are the circumstances? Why did he wish to build these machines? It's very quick, and it's sort of, without doing violence to the richness of any man's life, it's a sort of caricature, thumbnail sketch of his life, if you like. Okay, that's not Napoleon. It's Babbage in 1813, age 21, undergraduate at Cambridge, a spirited undergraduate, went there to study mathematics. There's a lesson in Babbage's study of mathematics, and that he was Peterhouse's crack man. He was a very accomplished mathematician when he went to Cambridge. He looked forward to having his puzzlements about calculus and continental theories illuminated by his tutors, and he found that his tutors were a staid old stuffy lot who weren't interested in continental mathematics, so he was quite a renegade. He arranged his own program of study, founded the Analytical Society dedicated to the reform of English mathematics, and which had quite an impact. Befriended John Herschel, the astronomer, a lifelong friend, George Peacock. But there's an indiscretion he committed, which is not widely known. And that is, he was Peterhouse's crack man. He was expected to be a wrangler, this rather obscure method of... and in order to qualify for sitting the highest... students were ranked according to ability by a preliminary set of procedures called the Acts, in which you have to defend, sometimes in Latin, a proposition against opponents. And he chose to defend the thesis that God was a material agent. And this was regarded as blasphemous, and he was disqualified, he was thrown out. He didn't leave Cambridge, but he qualified without honours. And this is, the reason I mention that tale is firstly to any students, they ought to be aware that principles sometimes have consequences that are politically damaging to their futures. This scuppered any prospect, it's scuppered, I'm not suggesting they compromise those principles, they just ought to be aware of their consequences. This scuppered any prospect of Babbage having an academic career. He couldn't get a fellowship. He left with an ordinary degree. He was a top mathematician, so he was granted a degree. And he later became Lucasian Professor of Mathematics, so it wasn't a disastrous thing for him in career terms, but it had one. The point about it is that it set a pattern, because that was not the only time Babbage damaged his personal political interests by public protests, sometimes ill-considered, and it's not as though he was alone in the radical views he held. John Herschel, George Valéry held similar views. One of the views was that they resented and resisted the notion that education was dominated by the church. University education was dominated by the church. None of them wanted to take orders. In order to take a fellowship, you had to become a member of the church, take orders. Babbage was hostile to this, but so was Airy and so was Herschel, and both became hugely successful contemporary science. I mean, Herschel was a model ambassador for science. They shared Babbage's view, but they were slightly more prudent in their public expression. And this pattern that Babbage set repeated later, far more damagingly, and actually affected the fate of the engine. So here I come again with this horrible medicine, looping back. We cannot separate the fate of these engines from who Babbage was and this proclivity he has for public protest. Most of his writings are written really more to protest than to persuade. He was indignant, he was highly principled, uncompromisingly principled. And if there is a lesson there, it is that there is a personal cost to high principle, especially if you're politically inept. Golly, at this rate, we're never going to get out of here. But that's, right, so that's Babbage 1813. Georgiana, his wife, married in 1814, just after he graduated, in defiance of his father. He ran away and got married in Teignmouth. He didn't get on well with his father at all. Georgiana tragically died in 1827, and Babbage was quite bereft, never really recovered, never remarried. This is Babbage, Lucasian Professor of Mathematics. So this is an engraving by Roth. Babbage occupied the Lucasian professorship from 1828 to 1839. This is around 1830-32. And it's a highly idealized. It doesn't look like that. You'll see from daguerreotypes, which I'll show you presently. The point about it is that he said that he was deeply resentful of the fact his peers did not acknowledge him. He was not recognized for what he did. He was convinced, it's perfectly clear, he had a very clear conviction that he had discovered something fundamental about the machine behavior, the stepwise procedure, algorithmic thinking. He knew he had seen something, and he was unable to communicate with others. He was deeply resentful of the fact that this was not acknowledged. And he said of his appointment as Lucasian professor that this was the only honor his country had bestowed upon him. And he said this without bitterness. He was deeply gratified for the chair. It didn't do anything. He never gave any lectures, never went to Cambridge. But that was a loophole in the regulations, which have since been closed. 1830, he published Decline of Science in England. This was an absolutely vicious, vituperous, sarcastic attack on the Royal Society, on the scientific establishment. Now, this was the self-same establishment that was to support him 3 times in securing government funding for his engines. So he had a fantastic habit of alienating the people whose support he needed. He somehow thought that being right entitled him to be rude. He personally attacked the officers of the society. He accused them of fiddling the minutes, of rigging the rules by which awards are given. He accused Davy of personally profiting from publications. It was a thoroughly indiscreet. It was not settled over brandy and cigars as a gentleman would. This was a public broadside of outrage and indignation about the deficiencies of the society. So again, we go back to that resonance of what happened in Cambridge. So that's, now in 1830 he published Decline of Science around the time of this thing. 1832 he published Economy of Machinery Manufactures. This was an absolutely groundbreaking book in political economy and one of his most successful books. It established him as an elder statesman of the industrial movement. It's an extraordinary volume, and it did much to, as it were, repair the damage that he had done with the scientific establishment. After the publication of Decline, he was a member of the Royal Society from 1816. After that, he never went to the Royal Society, he never attended any meetings. So in a sense, he'd excluded himself from the power base upon which science was operating. So that's Babbage. That's an oil painting by Samuel Lawrence at the National Portrait Gallery. That's Babbage in his early 50s. That's about 1843. This is Babbage as a man of science and letters, esteemed by his peers. He was very well known. He was a celebrity. He was well published. He published half a dozen very credible and not acclaimed, but well regarded mathematical papers. He published in all 6 monographs and 86 papers, miscellaneous papers, scientific and mathematical. So that's Babbage, if you like, at his height. Very credible figure, social lion of the London society, and esteemed by his peers. That's very intriguing. That's a daguerreotype by Clouday. And why it's significant for us is because this was taken at the time he was designing Difference Engine 2, which is the machine we'll spend, if there is any time left on. And there you can see he's still sort of combative, but he's wary. He's been through a lot, but he's still up there designing. He had, by that stage, almost given up the prospect of building engines, but he was carrying on designing them. So that's about, that's 1840, between 1849 and 1850, so he's in his early 50s there. This is Babbage 1860. It's the last known portrait of him at the 4th International Statistical Conference in London. It's what I call his Beethoven look. It's grumpy. It's a grumpy thing. The first biography of Babbage made with Moseley in 1963 titled her book The Irascible Genius. And this is a caricature that has stuck, despite the scholarship since. It is still the clearest and sharpest image of this man. And I'd say it's still, if one wanted a snapshot of him, it's irascible. Okay, that brief thumbnail sketch sort of traces Babbage from an idealistic student into, through an esteemed man of science, into a venerable grump. That, if you like, is a very brief account of his life. His father died 1827. 1827 was a staggeringly personally tragic year for him. His father, 2 of his children, his wife died all in the same year. He was, effectively had a breakdown. I don't know if they used those words and quite what the word means, but he went on a continental tour for over a year with one of his workmen and stopped work in the engines. He inherited £100,000, which is a staggering sum of money in those days. If you think that a steam engine by Stephenson, shipped to the States in 1830, the John Bull, cost off-the-shelf, brand new steam locomotive, cost £784 and 7 shillings. Inherited £100,000. In modern day terms, you have to multiply by about 30 to 150. So he was sort of near a millionaire. He was well able to afford to fund the construction of these engines from his own pocket. And to a large extent, he did bankroll the projects despite government money. Okay, that's enough of Babbage. The medicine's been taken. Thank you for being so gracious. And I hope that it has the appropriate and desired effect. and that you will all be cured of your obsession with technology. I meant that facetiously. It was, okay, why did Babbage design engines? What were they for? What was the whole movement about? That's a page of mathematical tables from Vega, logarithmic tables from Vega, 1794, typical of tables of the time. And the point is, how were these produced? These tables were produced by hand. I mean, clearly these are typeset, but there were 4 stages in the process of production of mathematical tables. Mathematical tables are hugely important. There were no devices that you could produce, do instant calculation at time and place of need. So almost anyone who needed tables, and that's insurers, journeymen, tradesmen, scientists, engineers, anyone who needed to do any calculation beyond anything trivial, including ready reckoners for fractions, multiples, squares, cubes, and all that. Absolutely reliant on printed math. The medium of communication was paper and print, and it's perhaps necessary to remind ourselves of that. There was one particular application of tables which was absolutely paramount, and that was astronomical navigation. Ships were reliant on tables for determining their position at sea. Capital and life was at risk. England was a major seafaring nation. The navy and merchant navy depended on accurate navigation. Shipwrecks were a very serious fear, and these were reported with graphic detail in the public media, Illustrated London News, for instance. And the number of gizmos and gadgets to prolong life at sea after shipwreck is astonishing. Scientific American has endless devices for keeping people vertical, for preventing fish biting you, for doing all sorts of things. And clearly there was a lot of public fear. So there was a deep insecurity about shipwrecks. Now, the few court-martials of ships going aground that I've looked at, none of them specifically incriminate inaccuracy of tables. It's always to do with the practice of navigation and all the rest of it. But there was this deep fear. And so the fear was that tables were riddled with errors. And the reason they were riddled with errors was, well, Dionysius Lardner looked at errata sheets. When errors were found, they printed errata sheets, and you could tell by analyzing errata sheets just how error-ridden tables were. And in a random selection of 140 volumes of tables, Dionysius Lardner found 3,700 errors printed in errata sheets. He hoots with uncontainable glee to discover that some of the errata sheets had error themselves. And he's utterly uncontainable when it turns out that the second errata sheet also had errors. So we had to print errata, errata, errata. So it was quite a credible position to hold that these things were riddled with errors. Why they were riddled with errors is because of the method in which they were produced. Tables were calculated by hand by people who were called computers. It's known that people were computers, they weren't machines, just as typewriters were people rather than things. And so firstly, there was the risk of human error through fallibility. We were very bad at doing accurate calculations, especially repeated, tedious things like repeated addition from differences, which was the technique used for generating these things. The second thing is you had to write the answers down in a table to give to a printer. So there was the possible error of transcription, writing the results down. Third source of error was typesetting. Each of these digits is represented by a loose type by a compositor. It's possible to put them upside down. They fall out. You put them in the back way around. There is no contextual thing to indicate. It's no more likely that one number is a 6 or a 7. It's not like a word where somebody can recognize an error. So there's no contextual information to indicate to the compositor that it's wrong. So error of calculation, error of transcription, error of typesetting. Thirdly, proofreading. How do you know the stuff's correct? And anyone who's seen a sea of tables and to give some idea of just, I mean, you might say, okay, it's not so bad doing that, but if you give some indication of that's the volume that page came out of, what confidence could you conceivably have if 2 people try to check tables of that kind? That's one volume of just logarithms and trig functions. So that's the problem. The problem is error in tables, and the solution for Babbage was mechanization, engines, machines. So that's the entry point, if you like. And the Genesis episode. How did this happen? Did it come in a flash of, a bolt of lightning and a flash of thunder? What? Something like that. He's sitting with John Herschel, his good buddy, in 1821, checking tables from for the Astronomical Society. And what was typically did, you gave the same set of calculations to 2 separate computers who, without collaboration, computed the results separately, and you compared them. If they were the same, it doesn't mean to say they were correct, because there are instances of 2 people making the same mistake. You had a high degree of confidence that they were correct. And Herschel and Babbage are sitting there in 1821, summer of 1821, in the rooms of the Astronomical Society, checking the 2 results from the sets of computers. And they are dismayed by the discrepancies. And Babbage, as it were, clasps his hand to his head and says, I wish to God these calculations had been executed by steam. Okay, that was it. That was the rest of his life. That phrase dominated the rest of his life. He spent the rest of his life, in one way or another, intermittently, but very intensively, trying to calculate, produce a mechanized automatic way of printed mathematical tables. Now, steam was a metaphor for mechanization. It wasn't necessarily that these things would be driven by steam. Nowhere else in any of his writing have I found any reference to any of these machines being driven by a steam engine. So steam was a metaphor for mechanization. It was the middle of the Industrial Revolution. England was the workshop of the world. So steam was metaphoric rather than literal usage of steam. Excuse me. So that was the start. He then became obsessed. He became so obsessed by these things he actually became ill. And he was advised by his medical practice to stop thinking about engines. He didn't. Right, what was the state of play at the time? Just how revolutionary is his conception? Just how revolutionary is his conception of these things? Well, it's probably well known that the earliest known mechanical calculation received a huge impetus in the 17th century. Willem Schickard in 1623 made his calculating clock, didn't survive. Earliest surviving calculator is Pascal's Pascaline, 1642. Sorry, that's an arithmometer. Where's the Pascaline? No, sorry, it's not there. That's an arithmometer. But 1642 Pascaline. The point about the Pascaline is that, and subsequent, Leibniz's later calculator of the 17th century, is that they were basically ornate curiosities. That's a calculator by Müller, 1784, to give you some indication. It's based on Leibniz's stepped wheel. And these were ornate curiosities. They were totally unsuited for routine, irregular use. That's a universal calculator, does addition, multiplication, does multiplication by repeated addition, and so on. These were objects of caused quite a stir. They were paraded through the salons of the elite and the aristocracy, stimulated huge discussions about mentalism and machines, but they were not workhorses for daily calculation. The arithmometer which we had there was the first commercially successful machine. It wasn't commercially successful much later. It was introduced in 1820, Thomas de Colmar. They were used in vast numbers, made by the tens of thousands later in the century. It took many, many decades before they actually caught on. Until they were introduced, this 1820s first commercially successful calculator, there were decades of development before they were accepted, before they actually ironed the bugs out of them. So 1820, just before the point at which Babbage conceived this great perception, that had this great revelation, that the answer, this invocation of steam to solve the problem of mathematical tables, this was what and that's a later one, I mean a cruder version of this, was what was it. Now the point about this is that it's manual. It relies on the continuous informed intervention of the operator to achieve useful results. You have to push the sliders, you have to turn the handle a fixed number of times, you have to lift the carriage, multiply by tens, you lift the carriage, shift it one decade over. You could make a mistake and shift it two. You have to write the results down, transcription errors, so there's possibility of operating errors. It's a manual calculator, relies informed intervention to get any useful results out of it. So that's the big first step, was automation, to embody the mathematical principle into the machine. And Babbage conceived of his difference engine number one, his first difference engine, which is in 1821, and that's what ultimately eventuated from it. He spent 10, 11 years on design and development of this machine. That's 1/7 of it. It's all that was assembled. About by 1832, he was losing credibility. He had nothing to show. He asked his engineer, Joseph Clement, to assemble something from the made parts, and this is what resulted. It's probably the most celebrated icon in the prehistory of computing. It has that position for several reasons. Firstly, it's a metrological standard. If you want to know how precisely you could machine parts, repeatability, accuracy of any kind of precision manufacture, you do measurements on this machine. It was made by Joseph Clement to the highest standards available at the time. So it's a metrological standard, so it's of museological and historical interest. It is also the first automatic calculator that survived. There's a handle on top. You crank the handle, you set the initial values, you crank the handle, you get results. Every time the machine goes through one cycle, it produces the next value in the table by method of finite differences, which I assume is completely familiar to you. And I think I've got a small trivial example to show just in case it isn't. All it does is by repeated addition evaluate polynomials. And we'll see how that does that. The point about it is that it's the first machine to successfully embody mathematical rule in mechanism. The operator does not need to understand the mathematical principle on which it's based, or how the machine works in order to get useful results. You exert physical energy and you achieve results which up to that point in time you could only arrive at by mental effort, by thinking. And the implications of this were not lost to Babbage and his contemporaries. They called it the thinking machine. The marvelous pulp and fiber of the brain had been substituted by brass and iron. He, Babbage, had taught wheelwork to think. This was, so said Harry Wilmot Buxton, a junior colleague of Babbage's. So the implications of this were not lost. I mean, of machine intelligence was not lost on Babbage and his contemporaries. So that's difference engine one. Difference engine number one. Yes. So high, about 2 foot high, about 8 inches deep, and so on. The full machine would be in something like 11 foot high, 8 foot deep, and weighed many, many tons. Many tons. We don't know. I can tell you about difference engine 2 specifically because we weighed it. And this would be vastly heavier. The difference engine 2 weighs 5 tons, and this was about 3 times the weight. This one is 3 times less efficient difference engine 2, 3 times more parts. So we're talking about 10 to 15 tons, estimated. Please.
I guess this was the first definition for artificial intelligence.
Yes, I would say that's one of the original artificial intelligence artifacts. Yes.
What was the effective MIPS value?
We've redefined the MIP. We've defined it as the crick. And I'll come to the crick, and I'll tell you exactly what a crick is. Crick is the name of the engineer who cranked the handle. We know exactly how many cricks these machines can run to. And there is a conversion factor. So that's difference engine 1. I don't know if there's time, but there's a wonderful thing. Again, it's history, so it's probably unpleasant for you. This machine featured in the development of the history of ideas in a way that is not specifically related to its technology, but had a huge impact. Babbage used it to demonstrate his theory of miracles. And I know this is dangerous territory, especially in an environment like this. Science was under religion was under increasing siege from science. Geology started producing, in the 1830s, geology started producing evidence that the Earth was older than theologists had actually led people to believe. And so there were rifts and cracks appearing in the edifice of religion. And the problem was, how do you reconcile rational science with theism? How can you both be a scientist and believe in God? And Babbage used this machine in a very ingenious way to try and reconcile those two positions. And you see, the problem was with miracles. You see, miracles are very good for religion. They're fantastic PR. Because you don't need a causal account. Science espouses the notion of physical cause, right? If God causes everything, there isn't a problem, because that's the explanation. Science says there's physical cause. Now, the problem was miracles are manifestly stressful for science because they are events without physical cause. So unless science addressed the issue of miracles, it was in deep trouble. And if you like, during this wrestling match for the explanatory scepter, they were competing with each other for the accepted view of the world. And Babbage had an absolutely ingenious way of showing that miracles, the discontinuities in nature, were not necessarily manifestations of divine intervention. What he did was he said, okay, Babbage was a social lion. His soirees, Saturday soirees, if you want to know what is going on in science, in literature, art, religion, you went to Babbage's soiree Saturday. They were the social events of the week. Everyone was there. Darwin, Macready, anyone you can think of was there. And the social intellectual elite of London, of English society, was at Babbage's. So Babbage used this thing as a party trick. It sat on his mantelpiece and he cranked the handle. What he did was he set the machine up to do something very trivial, like increment by 2. Yep. So every time he turned the handle, a number moved to 2. You know, that number was incremented to 2. And he'd do this, and very quickly people would become pretty inured to the expectation of incrementing by 2. So he'd crank the handle, would go by 2, 4, 6, 8, and he'd ask, you know, what do you think the next result's going to be? And it would be 2 and by go. And he'd do this endlessly. He'd do this 100 times. People began to get bored. The engine was rather trivial. And suddenly, without any intervention on his account at all, the machine would form a discontinuity. It would suddenly add 117. And he would turn to his people and say, you see, for you, the observers, that was a violation of law. It was a violation of the law of incrementing by 2. But for me, the programmer, I programmed that machine that after 150 iterations, it would do something discontinuous. So to me, the programmer, that is not a violation of law, but a manifestation of higher law, known to me, but not to you. By analogy, miracles in nature, discontinuities in nature, are not violations of law, they're manifestations of higher law, God's law as yet unknown. So, for Babbage, God was a programmer, and those in the software industry may be very flattered to know that. Okay, I apologize for the insulting triviality of the next example. Okay, why method of differences? The machine is called a difference engine because of the principle of, it's so called because of the principle on which it's based with method of finite difference. Everyone knows that the nth derivative of an nth order polynomial is a constant. That's right, calculus stuff. So the question is, what's special? Why is the difference principle so important? And the answer is that you can evaluate polynomials, which ordinarily, in the evaluation of the various coefficients, constants, the various coefficients of the various powers of the unknown, ordinarily you need multiplication, division, subtraction, and division to multiplication, division, subtraction, and addition to find the value of the coefficient of the multipliers. Now the point about doing direct multiplication and division in mechanics is monumentally difficult. It's something Babbage accomplished much later. The beauty of the method of finite difference is it allows you to find the value and tabulate values of polynomials using repeated addition. And this trivial example, and I apologize again for the triviality. Okay, counting numbers are x. X squared is the familiar table. Now assume that we've generated up to 36. We want to generate the table of squares. That's the object of the exercise. So it goes 1, 4, 9, 16, 25. Say we've got up to 36. Well, I mean, I apologize for all this familiar, but right. You take successive difference. 4 minus 1 is 3, 9 minus 4 is 5, and so on and so on. The first difference, the first column is the first difference. Second column, predictably, is constant 2. It's a second order polynomial. And second derivative. So by working backwards, you add 2 to 11, 11 to 13, 13 to 17, 36 to 4, you get 49. You get the next element of the table having performed no multiplication. Okay, that's a trick. Repeated addition, you can find the polynomial. Trivial example, it's x squared, but the point is that Babbage's machines, and the one we built, calculates to 7 orders of difference and 30 decimal places, right? So each of these digits is 30 to 31 figures long, and there's 7 orders of difference. So you can calculate, so the difference engine 2, for example, was designed to calculate and tabulate any 7th order polynomial, positive and negative coefficients, x plus or minus, any 7th order polynomial with all terms present to 31 decimal figures of accuracy. So that was the ambition, and that's no slouch even by modern standards. These were fixed point machines, but even a modern calculator, sophisticated as it is, although it overpowers ENIAC and all these other things monumentally, you still can't get 31 digits of significant figures out of it. So we shouldn't be back to E.P. Thompson's The Enormous Condescension of Posterity. This was no small accomplishment to conceive of an engine with that capacity. He didn't build them, of course, but we remedied that. Okay, these are decimal digital machines. They use the digits in order to 10. He considered all other number bases, including binary. He considered duodecimal, hexadecimal, 8, bases of 5. He considered all kinds of bases. Chose decimal for reasons we can discuss perhaps presently. The reason for this slide is really to show the attempts for why it was digital. Okay, it only acknowledges discrete states, whole numbers. So a wheel, okay, numbers are represented by figure wheels with engraved things on it and teeth on them. A wheel between 2 and 3 does not represent 2.5. It represents an invalid state. Now the point about it, these are not bistables. They're not metastable things that flip automatically once a threshold is exceeded. These are analog devices. The reason they're digital is the control system. And here's an example. You can see this roller tries to sandwich itself between 2 half moons as it goes round. That is how we digitized it. That roller locks and fixes it. Because it's a roller and rather than a wedge, it doesn't flip over once it actually goes beyond the threshold. But you can begin to see why it's digital is because that is what actually makes it invalid. If that is obstructed by one of those half moons sitting on the apex, the machine jams. So the machine jamming is a form of error correction, and it's a specific part of the control mechanism. It is intended, the discretization of the states is through its control, not inherent lack of stability, as you would be saying a modern threshold bistable or whatever. That's difference engine 1, 1822. Okay, Babbage is not famous because he's difference engines. He's famous because he was the pioneer of computing. His difference engines are calculators. You put numbers in, it crunches numbers the only way it knows how is by repeated addition. So it takes a column and adds to another column and so on. That's a calculator. It has specific functions, however elaborate. It can only do what it's programmed to do. The analytical engine is why he really has his claim to fame as the first pioneer of computing. And the analytical engine is just simply stunning and startling. I put that up there. It's not the analytical engine. It's the piece of the mill of the analytical engine under construction at the time of his death, small experimental model. The analytical engine in its minimum configuration between 20 to 30 foot long, 15 foot high, 8 foot in diameter. It would have been impossible to turn by hand. He talks about the minimum configuration would have 100 variables. He talks about variables, what he means is registers. A variable is a register which can take a different value. The minimum configuration would be 100 variables. That would be a machine the size of a locomotive, 20 feet, 30 feet long. He talks about machines with 1,000 variables and 50-digit registers with double precision arithmetic with 100-digit results. So we can see that his machines just in conception and physical size are a monumental leap, a quantum leap in conception, in logical conception and physical size in relation to what one means. It's like a jack in the box. He pops up in history with, as it were, without cue. So the analytical engine, if I can just stun you, with the respects in which it incorporates and embodies almost, I ought to be careful here given who's present, it embodies almost every single logical feature of the modern digital electronic computer. Ha! Right. And I challenge you to
Microsoft Windows? I don't think so.
I'll now list some of the features. Yes. Separation of store and mill. The memory and the central processor is separated, physically separated, and realized for the same reasons that of modern computer engineers as to why this was necessary. The capital investment in processing was too high to distribute, so you centralized it and then shipped the results in and out, shipped them back. Separation of store and mill. Second thing is conditional branching. If-then statements. If a particular condition was satisfied, it would take one or another actions automatically. It was programmable using punch cards. There were 4 kinds of cards: number cards, variable cards, combinatorial cards, and operations cards. The variable cards told the addresses in the store where it was go to. The operation card told what instruction it could do. It had a fundamental repertoire. A number card was a data card, and a combinatorial card told you how many iterations to do. So it was all programmable in this way. So it used program. It had an internal repertoire of instructions. It had automatic multiplication, automatic division, subtraction, and addition, and it was user programmable. You could string a list of instructions in any sequence you liked. You could iterate them. So it had conditional branching iteration. It had multiple processing. It talks about having more than processes. It had card punch output, printed output, graph plotting output. These are specific designs. This is not wishful thinking. This is not retrospective projection from the modern age. These are explicitly and specifically embodied in his mechanical designs. This is not the coded vagueness of Nostradamus. This is engineering. So when we say he was the first pioneer of computing, this is not a casual tribute. I mean, all these features are specifically embodied in his machines. There's pipelining, and I'll explain. There's another instance of pipelining. Microprogramming. You give it a single macro instruction, say do this, and it automatically executes the lower level instructions to execute that instruction. These are specifically embodied in these machines. So that's the analytical engine. I can show you some punch cards, an operational card and a variable card. These are the pasteboard cards. The larger ones are the operation cards, and the smaller ones are the variable cards, which tell it where in the store to find the material. The cards were based on the Jacquard loom, as is well known, and which was used to control patterns of weaves, automatic control of the pattern in woven textiles. That's one of the very earliest computer graphics. That is a portrait of Jacquard, the man who devised and developed that thing. And that is not an etching and it's not an engraving. It's woven in silk using 20,000 cards in a Jacquard loom. And this, again, had an interesting influence in the development of ideas. What it did, shading was regarded as an aesthetic quality, which was peculiar to craft and art. What this proved, because you could mechanize this and produce other copies of these, it showed that the industrial arts were capable of subtlety, which was hitherto considered the province only of craft and art. Now, this had a huge influence at the time to show that such subtlety was still within the province of mechanization at a time when mass production was actually beginning to compete with craft technology. And he had this hanging on his wall, and Prince Albert saw it, and it was a very well-known, celebrated piece. And precisely that, because it was mechanical and it embodied features which had hitherto been regarded as a property outside the province of dirty old engineering. Yes, there's one hanging in the Science Museum, in the Babbage Gallery. And you peer at it. I cannot tell with my, even with glasses, that the resolution of the weave. It is so fine that you cannot tell. I cannot tell it's woven. Okay, so that's Babbage's. Over for time. When am I supposed to stop?
We have at least 25 minutes to go.
25 minutes, fine. Okay, we can do more history then. Okay, Babbage failed to build any of his engines. He failed to build any of his engines. And the reasons for that are still hotly debated, and his life, in a sense, has become a kind of modern parable.
The engines he built were then incomplete engines.
Yes. He never completed any of his designs. He completed the designs, he never completed any of his engines in the metal. He built partial assemblies and experimental pieces. And the biggest piece we saw was the difference engine, that 2-foot thing. I would say that the fate of the rest of the parts, he made 11 to 12,000 parts of the 25,000 needed. The rest went to the melting pot. Used partly by his son. One was sent to Harvard University, in fact, small little assembly pieces. But the rest of it went to the melting pot. And all that was, the most substantial piece he ever accomplished was that piece I showed, difference engine number 1. It works impeccably to this day. All the control mechanisms are absolutely intact. And it's one of the most cogent arguments against Babbage's detractors, that had the full thing been built, it would have worked. But there was always this uncertainty, given that he had never completed one, and that is the sort of doubt that has always hung over Babbage's reputation. Was he an impractical dreamer? Was he an engineer of the highest caliber? And I hope we will have some answers within the next 25 minutes. Right, this is difference engine number 2. That's the machine we built. It was designed between 1847 and 1849. That is after Babbage had completed his major work on the analytical engine. So he'd already gone way, way beyond methods of differences and repeated addition. He had already managed to get machines to multiply and divide directly, which was an astronomically difficult thing to do. And he, during the course of the refinement of his ideas in the needs and demands of the analytical engine, he realized he could build a difference engine vastly more simply and elegantly. And this is like a masterwork. He produced no experimental pieces for it. It was like Mozart. He had conceived of it and he just produced a complete design. It's also the only complete set of drawings that was ever left, for reasons which I'll elaborate on presently. So that's difference engine number 2. It's 11 foot long, it's 7 foot high, it's 18 inches deep. It weighs 2.6 tons in its present form. What's missing is the printer. Okay, what I didn't say after the business about the tables was Babbage's conception was simply to eliminate all sources of error. That's calculation, transcription, typesetting, compositing, and proofreading in one go through mechanization. And the idea was that the unerring certainty of mechanism would ensure that there were no errors in calculation. If you could incorporate a printer integral with the machine, mechanically coupled to it, that is to eliminate the human from the information loop completely. You set the initial values, you turn the handle, what comes out is printed results. Then you not only solve the issue of transcription, but that of typesetting. And because of the method of finite differences, you also solve the problem of proofreading. Because each result is dependent on the previous result. If the last result is correct, you have a high degree of confidence that everything else is. So you need to check one value. So by using a method of differences and using automatic computation.
But what sort of books does it do you when you don't have copies?
Great. Absolutely. Having one copy is pointless because the whole point is to have a medium of communication. The machine does not only print a checking record in hard copy on a print roll. What it does is impress the results on stereotype plates or soft metal from which printing plates can be produced. Right? Now the bit that is missing over there is the printer. Integral to the concept of this engine is the notion of an automatic integral printer. And the bit that's missing there, for political reasons, we couldn't raise the money in time to finish in time for the anniversary, is there. And I will show you presently the first, we are now building the printer through the kind benefaction of Nathan Mervold. We're also building an entire replica of this engine and the printer for his house. And we have just done the trial assembly in the last few weeks before I came of the printer, and I will show you first images ever of the printer, at the trial assembly of the printing mechanism. It's massive, it's more complex, it's more interesting than the engine in many respects. And the answer is it not only produced hard copy, but allowed you to produce stereotype plates, printing plates from which, using a conventional printing press, you could then replicate results. Okay, I haven't quite finished saying what this is about. Okay, that's the machine. It has 8 columns of figure wheels. Numbers are stored and operated upon on circular figure wheels. I'll show you a picture of one presently. It's operated by turning a handle. That operates through a cam stack. There's your microprogram. You turn the handle and say, calculate the next value. The cam stack translates. That's 14 conjugate cams. They're geometric inversions of each other, 14 conjugate cams. Translate circular motion into lifting and turning motions, the intermittent lifting and turning circular motions required for the method of differences, which allow you to add a number from the right-hand column to the next column, to the next column, to the next column, and so on. So you enter the initial values from a table that you calculate by hand, and every time you turn the handle after that, you get the next result, which appears on the last column. So the information progresses from right to left. Now, at any given time, so the units at the bottom, the 30-digit number is represented in a column, that's a register. The units at the bottom, tens, hundreds, so on, all the way up to the top, 31 digits. So the constant difference, the last difference, if you're using a 7th order polynomial on the last one, that keeps its own value. It adds that number to the next one, next column, the next column, so on, all down the line. Now, at any given time, you've only got 2 columns that are effective. You've got 8 columns in the machine, you've got only 2 columns working. If you're adding 1 to 1, first column to second, second to third, at only one side. So during the cycle, column 1 will add to column 2, and then column 2 will add to column 3, and so on. Any given time, you've only got 25% of the machine working. What he used was pipelining. He adds or columns 1, 3, 5, and 7 to columns 2, 4, 6, 8 in the first half cycle, and columns 2, 4, 6, 8 to the odd columns in the second half cycle. You can then extend the machine to 14 differences, and the cycle time is independent of the number of differences. And as long as you offset the initial values, you have an ordering pipelining. 1847. Yeah. I trust that applause is for Babbage and not for me. So we've got microprogramming, we've got pipelining. Okay, the mechanics of it I'll go into presently, and I assume you're perhaps more interested in that than the history, but sorry, tough, you're going to have to live with the history. What else about it? Okay. That's one of the figure wheels. It has 4 decades. The reason is he needs big wheels. He needs big wheels because he has to have security. There are various security mechanisms. The whole thing is premised on the fact this machine cannot err. Now, Babbage, he has 3 separate security mechanisms. He challenges you. He says, you can walk up to this machine and it will calculate correctly. It will jam, it will break, but it will never deceive. And he is challenging you during an operation to walk up to the machine and try and derange those wheels. Now, that's a rather startling thing, because if you've got a wheel, whether or not it moves depends on whether it's added to. It can be added to in 2 ways. From the wheel on the right of it, on the column on the right, giving off a number to it, or it can receive a carry from below. Now, because whether this wheel moves or not is data dependent, the wheel cannot know, you cannot know in advance whether to free it up. So what you have to do is free it up for the window in which it can either accept a number from the right or a number from below. You would think that during that window you could derange it. Well, you can't. It is designed only to accept information from legitimate sources. And we didn't actually fully understand the mechanism by which that happened. But because the historical integrity, which is something I haven't spoken about of this construction, was such that we replicated even things we didn't understand. And it's only in the course of assembling this machine that actually we understood the monumental subtlety of the way he had accomplished that. And I'll show you the part that actually allows that to happen. So we answered a question that had hitherto been unknown. Why did Babbage build so big? There are other machines that are smaller that were built subsequently, which the reason is security mechanism. Okay, that's to give you some physical scale. That's Reg Crick, and I'll explain about the megaflops presently. Or I'll do it now. You turn the handle. That's in its part. It's constructed in public view. The public could speak to the engineers as they did it. And that's Reg Crick. That's Barry Holloway, the 2 engineers that had the major role in doing it. Okay, when you turn the handle, the machine performs in one cycle 7 31-digit additions. Right? It performs 6 calculations a minute. So one calculation takes 10 seconds. So one crick is 7 31-digit additions in a minute. And that's you need a multiply factor to get that in the megaflops. Okay, what was the informational datum from which we started this divide? Babbage left a complete set of drawings. There were 20 drawings and 4 tracings. That is the one that is perhaps most evocative of the shape of the machine. It's Bab A163. One thing you may notice is that the handle comes out from a position slightly below the main shaft of the bevel. Right, if you look at the next drawing, you can see the handle comes out directly from the main shaft. Right? We put a 4-to-1 reduction gear in. When engineers first looked at that, people who weren't Babbage freaks, looked at that drawing, they actually didn't understand how it worked. In fact, neither did we at that stage. And they looked at all these numbers of gear wheels and said it would be impossible to turn the handle. And these were people who brought in for advice, so we had to take the advice. None of the Babbage zealots could possibly conceive that their hero could have made a mistake of such fundamental, such a fundamental mistake. So they abided by the advice, and we put a 4-to-1 reduction gear in. It turned out the engineers were right, but for totally unforeseen circumstances. If we'd built the engine as Babbage had designed, we would not have been able to turn the handle, but nothing to do with friction. And I'll explain that presently. So the displacement of that handle, you can see it comes out one below, is to do with the 4-to-1 reduction gear that we put in. Now, one of the principles of the whole issue is that any variation in the design, any modification to the original design, had to be reversible. Otherwise, we would invalidate the historical. We had to resist the charge. You built Babbage's engine, but Babbage could not have. It would have been defeated the purpose of doing so, unless we could say, Babbage could have done this, but possibly by other means. So the machine was built out of bronze, gunmetal, cast iron, and steel. We did composition analysis on 1832 metals to find the best match, and there's only one instance in which we use a metal of a spring steel of a grade that Babbage didn't have, and that does not affect whether or not the machine works. It only affects on how fast you can drive it. It's an impact tooth, which takes quite a hammering. So the historical integrity was extended to the point of actual authentic materials. It's right. Now the point about this drawing is that you can see that it, in a sense, it logically completely defines the machine. Not this particular drawing, but its set of drawings. The shapes of the parts are known, the intention is known, but there is insufficient information. You cannot give a drawing like that to a workshop and expect it to make them. There is insufficient information. And there are several categories that are missing. Firstly, choice of materials. It doesn't tell you what the stuff is made of. It doesn't tell you anything about tolerancing, the precision with which parts need to be made. It doesn't tell you anything about finishing or methods of manufacture. Now, so these had to be provided by knowledge of 19th century machine tool practice. Tolerancing is a complete red herring. Tolerancing only has meaning if there is standardization, right? I mean, the fundamental notion of tolerancing. I mean, you cannot make a nut in Manchester and a bolt in London and expect them to fit unless there's some element of standardization. Now, there was no standardization in those times. Two lathes in the same workshop would have different master screws. You couldn't cut the same thread, a nut in one and a bolt in the other, which is why he was confined to one component manufacturer. We used 46 separate subcontractors. Babbage used one subcontractor, Joseph Clement. Joseph Clement made 11,000 parts in 10 years. We made 4,000 parts in 6 months using 46 separate specialist subcontractors. We unashamedly did not use contemporary tooling. We used modern manufacturing techniques. We used numerically controlled machines and computer-controlled machines to produce the repeat parts, but everywhere we were absolutely scrupulous to ensure that no part was made with more precision than we know from measurements Babbage was capable of achieving, but possibly by other means. So that's our defense. We welded where Babbage would have forged, and we dressed the weld to make it look like a forged part, not to deceive, but to give the visual authenticity of the appearance of the machine. We could have cast the figure wheels instead of machining them. We did so to get the bright finish. We paid £20,000 extra to do that, so that when the machine was looked at, because 90% of the message of this machine when people view it is not to do with the specifics of the technicalities. It's actually to do what does a 19th century machine, calculating machine, look like? What was it the Victorians never saw? Okay, now there are several interesting things about the drawings. One is there are errors in them, and there's a serious curatorial dilemma. If you make a deviation from the design, then in what respect could we claim we built Babbage's engines? If you do not make the deviation from design, in full knowledge the engine's not going to work, why build a piece of sculpture? And there are various categories of error. There are redundant assemblies. There are assemblies which are exquisitely beautiful and do absolutely nothing. There are omitted assemblies, and these are all to do with boundary conditions. All the errors usually occur on the boundaries. For instance, I'll go into that later. I'll show you the most obvious one. There are inconsistencies in dimensioning. There is the same part depicted in different dimensions on two drawings. You have to resolve that. You cannot say we're going to make it the way Babbage intended. If the same part is, what do? You make it halfway between, you make two of the same kind and transit. I mean, you have to resolve that. And so one of the big learning issues of this project was you cannot regard these drawings as some kind of sacrosanct ideal of perfection from which any deviation would impugn the historical integrity of the thing. What became very clear to us is we were resuming a project that had been intermitted 140 years later. This was the continuation. If Babbage had taken these drawings off the drawing board and gone to the workshop, he would have hit exactly what we hit. So the issue was not, what are we violating by making any design alterations? The question is, what would Babbage have done when he found this? And we applied no solution that we had not found Babbage had used elsewhere. He never uses slotted holes. He never uses grub screws for adjustment. These are monolithic machines, completely integral. There is no possibility of debugging this machine. You cannot isolate the drive from the calculating section. If you want a movement, he makes a fixed link, puts fixed, if you want to have a movement a different length, you make another link. There is absolutely no adjustment in the machine. Setting them up is a total nightmare. They had never done it. They had never thought of ISO. When the machine jams solid, which is part of its error detection, if it's jammed solid, you don't know where to start. There are no test points. You cannot isolate the drive. You go with a screwdriver somewhere and you fiddle. And you hope for some play. If there's no play, you go further down the machine. When you find some play, you work backwards till there's no play, and you then look. It is absolutely hair-raising. There is no method. They had never built a machine of this complexity. I absolutely believe if they'd done so, they would have used a modular construction of some kind. So we were breaking new ground, and what became very evident is that we were actually continuing an intermittent process. We were not actually building, there was an absolute interaction between what we were doing. This was not the distance of history working through, as it were, the diachronical kit gloves. Okay, just to give you some example of one of the issues we had to resolve. Okay, the printer that's being built is this huge section on the right here, which is part of the control mechanism of the machine. Okay, there's a digression. I know there isn't time for it. I say the print is a part of the control mechanism. If you're turning the thing, you set the initial values up. The moment you've turned the handle, the machine is no longer in the state that you set it up. It's in an unknown state. If you overrun, the printer gets to the end of the page. If you overrun, you've had it. You have to go and redo the whole thing because the machine will then be set up to produce the first wrong result on the beginning of the next page. Now you're at this end of the machine, the printer's on that end of the machine, you're not counting, you have no index counter, the machine has an index counter, it knows how many calculations are, but the printer knows when it's got to the end of a page. What it does is drop a ball into a scoop which moves, pulls a lever, there's a piece of catgut which runs along under some pulleys which goes up into a scoop cam. And all you do is turn, and when it gets to the end of the page, suddenly the hand becomes free, the drive is broken through a scoop cam, a scoop clutch, and the machine freezes in precisely the state it's needed to change the plate and resume the next time. Is that a reference to Microsoft again? Okay, just to give you some idea of some of the informational issues we had to resolve. You can see that the pitch, that's the separation of those columns, is all the same until you get to the second and the third. Excuse me. The separation between the second and third column is different. Okay, is that significant? We're building Babbage's engines, we're going to better put that space there. We think, well, hang on a minute, there's no coupling. Is there some special significance to the first two columns? Well, there isn't if we understand that these are just differences, they replicate the mechanism. Well, you think, okay, is there a plan view of this thing? If you look down from the top, would this resolve the issue? And indeed, you look at the plan view. Why is there no plan view? There. There's the plan view. Okay, you can see how monstrous the printer is. It weighs another 3 tons estimated, which brings it up to the 5. You can see if you look at that, you can see that there's a discontinuity in precisely the same place. That's looking at the engine from the top. We're looking between column 2 and column 3, and you can see there's a discontinuity there. There's a little fudge there. Well, we puzzled long and hard. We didn't want to violate it unnecessarily, but equally we didn't want to build something we didn't understand. And we puzzled over this, and the conclusion we came to is that the draftsman had started on the left on, say, Monday, and he'd worked all the way, and he started on the right on Thursday, and he worked all the way, and he got to the middle, and he said, the hell with this, I'm not doing this over. And he got the pitch wrong. And there was no more significance to that layout error than a drafting error. There's no other conceivable explanation for this. So that was, but those were, we took this very seriously. Was there some deep significance to the separation? Okay, that's one of the more obvious ones, but there are vastly more subtle ones of the kinds of, okay, that's the cam stack and the chapter wheel. Right. That is another drawing. That's to indicate the kind of absence of information. I mean, there is no, it describes the drawing, you can logically understand it, but there isn't information about methods, choice of materials, method of manufacture, finish, and tolerancing. Tolerancing the red herring, as I mentioned. Okay, now one of the security mechanisms I should mention, because it has sort of another analogy to electronic computing, is the way the machines lock. I don't know if you can see there's a wedge. There's a wedge which drives, actually there's a bit of drawing of that. It's slightly expanded in the next one, I believe. Yes. That is the guts of the engine. That is what is clever about it. Now, the calculators up to that time had 6 to 8 digits in them. The worst case of, okay, the problem is carriage of tens. How do you do that? That's the actual guts of the machine, and why it's so elegant, why he could extend registers to 30, 50, and 100 digits is because he'd solved the principle of successive carry. All the calculators up to that day had 6, 8 digits, maybe up to 12, and the reason for that is, the worst case is if you've got a row of 9s and you add a 1, you have to propagate the carry, ripple through domino carry, it's called. Yep. Now, if you're running with dials and you've got 9, 9, 9, 9, 9, and you turn the last one, you have to actually drive those wheels from the force derived from the last turn. They didn't have the materials, you couldn't do it. There was no successive progression way to do it. What he did was he separated the addition cycle from the carry cycle by using memory. He used latches. I mean, he talks about 1 unit memories. And he did this entirely mechanically. Now, what's clever about this machine is once you separate addition from carriage, you've actually solved the problem of force, but you distribute it in time, basically. You don't apply all the force in one go at one point, you distribute it in time, and that's successive carry. And the most visually dramatic and attractive feature of this engine, as you will see on the video, is this progression, this dancing DNA of these rippling helices that we will see. Now, this is the mechanism. You can see that's the plan view of the helix, that little fairground thing with the lozenges on the end. One of the security mechanisms is, that's a figure wheel. The way you lock it is you have a wedge. It's like a sword blade which runs up the column and jams itself between the figure wheels, and it locks them. And there's a wedge. That's the wedge here, the plan of the wedge. You can see up there. It's a wedge which drives in. So the wheel is only freed within the window in which it can receive information from alongside or below, and it comes out and it's free to move. It's locked in other respects during the window in which it's able to move. And that thing drives its way in. And the reason the machine couldn't be turned is because the pressure angle of the cam that drives that thing, because it comes in and goes out very quickly, the pressure angle, that's the steepness of the side for the thing to be followed, was too steep. And you actually couldn't drive the handle past this thing. And I'll show you pictures of that. But the point about this is that one of the security mechanisms is this lock. Now, if a wheel deranges very slightly and the wedge can still go in, you've got a pulse shaper. It restores the slight derangement. If it goes up to 2 1/4 degrees out, it's going to come end onto a cog and it will jam. And that says this wheel is in indeterminate state. It's no longer a digital machine, it's in indeterminate state. And that is how the control, we saw the half moons with the roller that's sandwiched on the first difference engine. The way it's done here is through wedges and controls. And that slapping sound you'll hear is actually the locks coming in and out. The reason for that drawing is to show you the difference between the Babbage specification of that part, which is that part up there, which is a carry lever, and the amount of information you need to specify a modern piece part. That's the most complex piece. There are 210 of those, left and right-handed. And that's the amount of information you need to specify a part of a modern machine tool shop. And you can see the sparseness, the richness of Babbage's drawing, but also the sparseness of manufacturing information. Now, we had to produce take these 20 drawings and produce piece part drawings for all 4,000 parts of this thing, and that took another 50 drawings to do, and everyone had to be specified. That's a modern drawing. That's the part up there on the top right, and that's typical of the 50 drawings that were made. That's 50 just for the calculating. There are another 50 drawings for the printer. Okay, that's the same, that's the plan. Okay, there is a major error. There is a major error in the design. It is not a logical error, although we didn't know that at the time. I'll go back to this mechanism. That is the guts of the engine. This figure wheel column adds to that figure with an intermediate sector wheel, so you don't get non-destructive transfer. If you have a wheel and you rotate it to 0, it will transfer its number to the next wheel, but you've lost the number, so you have to restore it. So the intermediate wheel, sector wheel, restores the number, uncouples from the other one, and then restores it. And you'll see that cycle working on the thing. There's a fundamental error. I don't have a pointer. You can see that curved nib over there, on that wheel just up there. That nib is what is nudged when a wheel goes above 10. This is the successive carry mechanism. So when a wheel goes above 10, a nib knocks that curved nib and it latches through an indent. I'll show you a computer animation of it presently. The point about it is that that mechanism can only work if the wheel turns for you anti-clockwise. The staggering thing in the designs, if the wheels go the wrong way, the mechanism can't work. It is absolutely fundamental. And this created a terrible crisis, because the issue is, was he using some complementary form of arithmetic we didn't understand? Was this a method of preventing industrial espionage? Was the error deliberate? And we racked our brains about what the solution might be. There are 3 solutions. You can lengthen the cycle.
I'm sorry to interrupt. We've got a slight logistic problem. We can have this room as long as we want.
Yeah.
So you can talk for half hour, as long as the audience is here. But we lose the ability to show your video in 10 minutes.
Yes.
So if you're going to get to your video within 10 minutes, I think we'll be fine. Otherwise, we should run that now. And then
We got 10 minutes from now.
Within 10 minutes from now, they close down.
Okay, the video is 5 minutes and a bit.
Okay.
Do you want
So if you can start that within 5 minutes?
Fine, will do. Thanks. Okay, let's step along. What was I talking about?
The wheel's going that way.
Wheels going the wrong direction. Okay, there are several ways you can do this. You can make the wheels go the other way by changing the control mechanism. You can insert an intermediate wheel that reverses the direction. Or you can mirror image each alternate axis. You can see the thing is biased to the right. Each alternate axis you bias to the left, you can do it. The implications of biasing it, of mirror imaging it introduces a 2 1/4 degree shift. And the reason for that is a peculiar one. It's something Babbage never foresaw. If you join the center line of that thing to that thing, you'll find that the center line does not go through the middle of a tooth. It goes to the right of the tooth. So if you mirror image it, you get a tooth where there should be a gap. The result of that is you have to turn the whole thing 2¼ degrees, and the problem is, how do we know the damn thing would work? And so that was the problem was there's a major design. It's not a logical error, it's a layout error. Second thing is what's the solution? The solution was mirror imaging. So we had to actually redesign the whole thing and take account of this 2¼ degree shift all the way through.
Did you have a 3D modeling tool that you used to find this stuff out?
I'll show you. We built a trial piece to verify the fundamental mechanism. Sorry, it's a back to front slide. It adds a 2-digit number and takes account of carry. Now, it's not automatic. You manipulate the rods and levers from the top to actually execute. It's an 11. The cycle has 11 separate stages in it, and this is what we built, which is the first section of the engine ever built to verify this new arrangement, this new configuration. We learned something very fundamental about the psychology. Okay, we were also trying to get funds, and I haven't spoken anything about the politics of what we're trying to do. I mean, there's a bunch of lunatics in a back room trying to do this stuff. And the question is, how do you attract attention? And we discovered something fundamental about the psychology of what we were doing. We found that if you want to convince somebody that something is made accurately and precisely, you make it shiny. And that's a legacy of instrument making, where precise things were polished. Now, we got practically no attention for this project. We put it in front of trustees, and they were sort of dutifully respectful and all the rest of it, until we polished the top plate. And then it got on television, they ran credits past it, they put it on the dials, the trustees want to give us money. Okay. They're the beautiful, okay, this is the helical mechanism that I showed you a plan of. They're objects of beautiful elegance in this machine. That's the helical mechanism, which does the successive carry. The successive carry is very interesting, so I'm going to tell you about it. What happens is the thing in its addition cycle adds all in one go. All the 31 wheels are meshed to the 31 wheels via the sector wheels, and the addition is done all at once. If a wheel in any decade exceeds 10, it latches the thing using an indent. What happens then, each of the positions needs to be polled, right, in succession. And how it polls it is tipping the thing, that as the thing, as the wheel turns, it knocks the latch. The latch has a lever. The lever puts it in a particular position. What happens with this thing, as it rotates, it polls each position in turn. It's displaced in a fixed angular position and polls each lever. The way it polls it is it sweeps the position. If the lever is set, that's warned, it intersects. And the locus of the two intersections nudge it, and it nudges the next wheel up. If it is not set, it misses it completely. So there's a conditional polling which does the successive carry. It's a ripple through carry, so a bottom carry can progress all the way up, and it can handle secondary carries that result from carries, because it rotates twice. So that's how the carry mechanism. Now the force on that thing at any given time is never more than it takes to move one wheel. That's how you can extend these things to. Okay, I think what we should do is, let me just check to see what's there, and I think we should run the video. That's another piece of piano. Okay, just the back of the, that's the carry mechanism assembled at the back of the machine, and if you think that's impressive, have a look at that. And if you think that's impressive, have a look at that. And if you think that's impressive, that's the Sunday Color Supplement version. That's the back of the machine with its those double helices, which rotate, which you'll see. Okay, I'll suggest what we do now is run the video, and you'll see the machine running. Okay, we need to kill the slide projector.
Modern technology.
We need some sound with that, because the sound is actually quite distinctive. There we go. Okay, that's that slapping sound. Those are locks going in and out. The reason it makes a slapping sound is they're driven bidirectionally. The reason for the conjugate cams is it drives it positive, it drives it negative. And the slapping sound is the reversal of the drive and the engagement of the thing. Sorry about the quality. It's transferred to NTSC from PAL VHS. And that was Reg Crick performing a crick. Okay, that's not a very clear shot. That's the bell cranks doing the lifting of the axes. Okay, that you'll get a better perception of what's going on there. This is the front of the machine. As you watch, if you sort of blur your eyes, you'll see the shifting of 1, 3, 5, 7 and 2, 4, 6, 8. You see movement in every alternate axis. Those are the figure wheels. Giving off, restoring. Giving off, restoring. It's all it does all the time. Adds, restores. Adds, restores. This is number crunching. And I don't know what the operating system is. What's that? I think Eric Drexler would like us to believe that. Yeah. The way it engages the columns is by lowering and raising the sector with the intermediate sector wheels. You get some impression of that's the full frontal of the engine as you look at it, of the calculating section. What's that? Yes, very clearly. You estimated the maximum speed which at the peripheral of a gear, and I think it's 10 feet a second. Okay, that's the bevel gear, that's the cam stack, and that's, if you like, a microprogram. That's the conjugate cams in pairs, 14 pairs of conjugate cams turning. You can see there should be a close-up of that shortly. You'll see the cam followers. It's not a reproduction, it's an original.
How many person hours or person years?
God knows. Okay, it costs £300,000 of direct costs. That's excluding my time, research time, staff time. That's what we had to pay for engineers to have parts made and to assemble them. 2 engineers and parts. You can see there, that in-out is the locks going in and out, driving those sword blades which come in to do the locking. And you can see the pressure angle on that is very, very sharp. That's why we couldn't turn the handle. We had to use a mechanism that Babbage used elsewhere to relieve the weight, to relieve the load. You couldn't extend the cycle. The cycle is terribly crowded. Those are the helices. That's the successive carry going up. And what I say is, when it looks like that, who cares where it works? That's a good question. It jammed absolutely incessantly. In fact, it was almost impossible to complete cycle while we were phasing it. Everything has to be phased, and then it's hardwired. You drive a pin through and lock it. Parts broke, snapped. It was impossible. It was absolutely very frustrating business. Once it worked correctly, it has never gone wrong. It's never needed any correction. It's pinned, it's hardwired, it can't budge. We run it when anyone asks for. In the first year of the anniversary, the 1991, the bicentenary of his birth, we ran it twice a day as a matter of routine. I think we can perhaps kill the video.
What would it take for a full set of coefficients from scratch?
Sorry, say that again?
How long would it take, so to speak, to boot the machine, enter all the coefficients from scratch, to run a new...
Including the calculation or excluding? Set up. 10 minutes. 10 minutes. Yeah. Sorry, there was a question which I didn't finish answering.
Oh, how often do you run it?
We ran it twice a day as a matter of routine during the anniversary year of the exhibition, and now we run it for anyone who expresses interest.
I was there in September of '93. So who would I have asked to speak from?
93?
Yeah.
You don't recognize me? No. Okay.
It was on a Sunday.
And you saw it running?
No, I wanted to see it run.
Ah, okay. My
I had the
assistant.
room all dark and...
Oh, how sad. Sunday's difficult because unless we have explainers who do this on weekends, any weekday, either myself or my assistant will demonstrate the machine to you. Even if you're an individual, you don't need to be a group or by arrangement. If we're there, we'll do it. We're going to change that. We're going to have, now that we're building the printer, we're going to actually, I'll show you the slides of the printer. We're planning on having the printer run and print out using a conventional 1838 printing press and give results out. And that we tend to do that as fixed demonstrations where there'll be fixed demonstration times. So I think if that's the end of the, is that the end of the televised proceedings? Seems so. Do we need a decision about whether you want any more? Do you want to hear about the printer or not? Or okay. Right, we can relax now. We can talk dirty. Okay. This is to give you some idea of of some of the information density. The photographs, the images I've shown you before are some of the best ones. They're the ones that are most evocative of its shape and the ones that are most meaningful in terms of internal mechanism. But not all of them are so immaculate. That's an example of where they didn't have automatic ways of producing tracings. So what they do is draw one view over another view and over another view and rely on dotted lines to present hidden edges. And that's, if you like, some of the most, and so the point is the thing becomes impenetrably dense. And there were some issues which we actually could not resolve. The question from that drawing is whether the framework is one piece, is one cast bed, or whether it's made up of multiple things. And actually we were not able to resolve that. So we had to make decisions based on knowledge of 19th century machine tool practice. We are fortunate in having a chap called Michael Wright, who's stepped straight out of the 19th century. Instead of phoning Babbage, you just go and talk to this guy, and he knows everything there is to know about 19th century machine tool. You walk into his basement, it's like going to see Clement. And so we relied on him very heavily on what materials would Babbage have used, what was the composition of gunmetal, what, all that stuff. And what size castings would they be capable of making? You see, they didn't have planing machines. They didn't have long bed planing machines. Now you just make something very rough and plane it and get the precision that way. But their casting techniques were vastly more evolved than ours. Because they didn't have planing techniques, their casting was vastly better. And so the question is, we may not be able to cast beds that precisely, but what we do is plane them. So what we did was make them out of separate sections